Hey friends, this is Ripak from Mechanical Engineering. Today I am going to explain ANSYS Fluent. So let's get started. To explain ANSYS Fluent clearly, I'll take a problem. So let's see the problem. This is the problem. Let's demonstrate that a cold fluid at 293.1 Kelvin temperature flows into the pipe through these spaces, large space, and a warmer fluid with warmer temperature at 313.15 Kelvin enters the smaller phase. There mixes the mixing elbow. So to design this system properly, I have to predict the flow field and temperature field inside the pipe. I'll predict this by ANSYS Fluent. So at first I have to design the system. To design a system there are many software. You can use SOLIDWORKS, ANSYS Design Modular, ATM or AutoCAD. I'll design this in SOLIDWORks. Design in SOLIDWORks. Click on new file. Choose it. Diameter of large inlet navigate in the focal path of the slave. It will be dropped in. Let's take a circle. This. From the figure, I find that this length is 200 millimeter. This also 200 millimeter. Calculating this, I find that the particle distance between these two lines is 950. Okay, now flip it. Save the file in this channel. Now I will create the small embed file. Diameter of will record this 5 millimeter. And next red and 425 millimeter. To create a spectacular system, I will change the appearance. Just create it spectacular. No, it is not necessary, but to make it spectacular, I have changed its appearance. And that's all about our system. Now I have to save it. Note that I'll open it in ANSYS, so I have to save it in a form that I can open it in ANSYS. If I save it in SOLIDWORKS format, I can't open it in ANSYS, so I have to save it in a special format so that I can open it in ANSYS software. So let's see the procedure. I will name it Talbo project. Talbo project. Here is the special format, IGES.IGES format. Save it in desktop. Okay. This is ANSYS workbench. Now I solve the problem with ANSYS fluent. So let's start. Follow the instruction very carefully. If you miss any instruction, it can impact in your project currently. I repeat, follow the instruction very carefully. Drag fluid flow fluent and drop here. A red colored box will appear. Named it Talbo project as before. You can see that it's asked for a geometry. Let's import or create geometry. As I designed the system, so I will import my geometry here. So let's import. My file was Talbo project app. You can see this, it appears there. Or you can browse your files in your file location. You know that I save it in desktop, so I find it desktop. Click here. Okay, now I will edit my system. Edit means simply I'll create a data symmetry. Now I'll generate imported body. This is my body or system. I will I'll generate a symmetry or plane of symmetry to the middle of this body, to this line, accurately to this line, and accurately to this line and this line. It's a plane, and you can see that this plane exists in ZX axis. So I'll create a plane of symmetry in ZX axis. Go to tools and hit symmetry. Now I'll generate my symmetry. Okay, all done. Check the unit, change it into millimeter. Now I'll close the design modular as I have made my symmetry. You can see that the plane of symmetry here. Now I'll generate mesh in that body. So let's create. ANSYS meshing software is open. This is my body. I'll generate meshing in this body. Before generating mesh, let's create some name selection. It's very important in this project. From the problem, you know that this is large inlet velocity. Let's name it large inlet velocity. And this is our small inlet velocity. Let's name it. This is our plane of symmetry. Now let's create this name selection as symmetry. This is our pressure outlet. Let's create this name selection as pressure outlet. Now we'll name the whole body with fluid. Let's change the selection method to body. Let's create name selection. This is fluid. Okay, my name selection is complete. Now we'll perform meshing. Hit mesh. Check physics preference to CFD. That means computational fluid dynamics, and solver preference to fluent. Now go to quality. Change the smoothing instead of medium to high smoothing, change in inflation to use automatic inflation, change it none to program control. Okay, now I will insert a body sizing. In body sizing, I'll just change the element size into my desired size. Input 5 mm as element size. Okay, now let's update our mesh. Hit mesh and jump into update mesh. Okay, our meshing is done. Close meshing. Now go to setup. This icon means a refresh is required. Let's go to setup. Check double precision is heated. Okay. This window partly changes unit into unit of length to meter to millimeter. Now I will check the meshing and mesh quality. You can check meshing and mesh quality also here. Jump to setting up physics. Check this option. Heat energy. Click to discuss. Heat into K epsilon method to equation. Check K epsilon model standard model and near wall treatment. Check it enhanced wall treatment. Okay. Now I'll add material which is water. So let's add the material. Name it water. Name it water. I inputted this value according to my problem. In the problem, the values of this parameter is given. Heat, change or create. It asks me change or create mixer and override here. Hit no. Now close it. Now go to zones. In zones, hit cell zone. Now I'll edit fluent. My material was water, so I'll active water as my material. Okay, well done. Close this window by clicking OK. Now I'll go to boundaries. I'll edit large and small inlet velocity, and I'll input some values according to my problem. So let's start. Velocity specification method. I'll specify my velocity specification method by component system. Now let's see in this window. See this window. This is my large velocity inlet, and this is my small velocity inlet. Direction of large velocity inlet in this window equal to direction of large velocity inlet in this triad, which indicate minus z direction, and direction of small velocity inlet in this figure and this triad. Comparing this direction, we notice that the direction of velocity of small inlet velocity is equal to plus x direction in triad. Now we'll input our values. Velocity, the value of large inlet water is 0.4 meter per second, which direction is minus z direction. So input the value of water minus 4 meter per second in large inlet velocity, minus 0.4 meter per second, and specify methods include intensity and turbulence, hydraulic diameter. From the problem, we know that the turbulence intensity is 5% and hydraulic diameter is 100 millimeter, and the temperature was 20 degree. That means 293.13. Okay, large inlet velocity is completed. Now jump into small inlet velocity. Hit edit. Velocity specification method as before. The velocity was x is to 1.2 plus of creation. The diameter was 25 inch small inlet velocity, and temperature was of 40 degrees Celsius. That means 313.15 Kelvin. Now jump into solving. Specify the method of solving. Instead of least square cell based method, we will use Green's node based method. Okay, hit disable in the reports for check the plot is activated. Now I will insert a surface report by clicking in definition. heat space at maximum. You can change the name. Instead of report def 0 by following naming system: heat report file, heat report plot. Keep frequency in 3, temperature and set temperature, and partly deselect all these surface and select pressure outlet surface. Okay. Now hit initialize. Check case. Okay, it's okay. Just hit to close. Now I'll calculate for 300 times. Let's start calculation. Fluent calculating the data according to the values. After the calculation, we will jump into post-processing to see our output. We can also discuss our result or outcome of this problem in ANSYS CFD post in the result section, but it is easier to discuss result in Fluent also, so I will discuss it in Fluent. That means here. Its output for pressure outlet surface or faces, indicating temperature. Okay, my calculation is complete. Post processing to analyze our outcome. We can perform this in several methods. You can click vector, contours, curve lines, particle tracks, or different kinds of graph. I will analyze it by contours and path lines. So partially go to contours. Follow the instruction. The problem tells us to find flow field. So to find flow field, partly we will go to velocity section and in symmetric plane. So let's display this. You can see this in contour. This is our velocity field. Here the velocity in this large inlet velocity was 0.4 meter per second, so it is smaller velocity than small inlet velocity. in this section the velocity was 1.2 meter per second. So water has higher velocity and water has smaller velocity mixing in this portion, and resultant velocity you can find here by analyzing this. Now let's see the temperature field. It's our temperature field. In this portion temperature of water is 20 degrees Celsius, and in this portion temperature is 40 degrees Celsius, and you can see this, the temperature is gradually decreasing. Let's see the pressure. This is our pressure. You can see that the pressure is higher than any other space in this system. Now let's go to preference. Firstly, we'll see the velocity, that means flow field in symmetric plane. You can see the output in all of this surface, but for less time I just use plane of symmetric plane. Let's pulse. Okay, now let's see the temperature field. Change it to temperature. Hit pulse. This is our temperature field. Okay, it's all about the problem. Friends, in this video I have tried as much as possible to explain ANSYS CFD fluent. In this tutorial, portion of ANSYS workbench were used to compare the fluid flow to slightly different geometries. ANSYS design modular and SOLIDWORks used to create a mixing elbow geometry. ANSYS meshing was used to create computational mesh. ANSYS fluent was used to calculate the flow field and temperature field. We can calculate or analyze the result in ANSYS CFD equation, named after result the solution in ANSYS. Hope that you can get the tutorial. If you have any problem, please drop a comment with time duration, and don't forget to respond.